Hello everyone. So let's look at today's lead code question. 129 number, some root to leaf numbers. Okay. Um, you are given the root of a binary tree containing digits from 0 to 9 only. You are given the root of a binary tree, root of the binary tree. Okay, from 0 to 9 only. Each root to leaf path in the tree represents a number. For example, the root to leaf path 1, 2, 3 represents the number 1, 2, 3. Root to leaf. Oh, root to leaf 1 to 2, 1 to 3. Return the total sum of all root to leaf numbers. Test cases are generated so that the answer will fit in a 32-bit integer. A leaf node is a node with no children. Okay. So the sum here is 1 2 plus 1 3 2 5. And here it must be 4 9 5 plus 4 9 1 plus 4 0, right? Yes. And the number of nodes in the tree is so there is at least one node. It can go up to 1000 nodes. And note that value it can be 0. Okay, it will go only from 0 to 9, and depth of the tree will not exceed 10. Okay, I got the question. So how to find it? 2 and 3. So when I looked at this question, then I just I think that it is pretty straightforward. I can do DFS, I think. So if it is 495, then I just needed to know 495 49140, right? So yeah, it means that, okay, I will draw a bigger tree here. 490 and 51. So I can just do DFS, isn't it? So I can go from 495. So it means I found a leaf. So whenever I find a leaf, then I can go back and attach. So whenever I go back, then I can just do 495, and then whenever at every node. So suppose if there was like 3 here, then at node 5 it would be just 5 3 only. What I'm thinking right now is, will if this is the case, then will it be 495? Will, oh no, because 5 is just, yeah, what I was thinking is, can it be 4? Should I also consider 495 because there is null, right? Because there is null here. So should I consider 495 null as well, or should I just consider 4953? That was what I was wondering. But I think I do not need to consider a leaf that is a null, leaf node that is null, right? Even in this example also, yeah, in this example there is no every node is a complete. So in this case, should I consider 495 as a 495 null as a root to leaf value? Root of the node, each root to leaf path in a tree represents a number. I'm not sure. A leaf node is a node with no children. It is a node with no children. So should I consider null as a leaf node? No, I don't think so, because I can also see the example. So if this is the case, 49051, and suppose 5 as 49051, and suppose 5 as children 3, then what is the answer? The answer is 1389, right? So it is 4953 490513. What kind of tree is this? Is this tree? 490513. If this is this tree, I don't think so. Anyway, I was just trying to see if I was just trying to input this as my test case, this tree as my test case, and try to see if, you know, try to see if this is also considered or not. But I think that I did not translate this into a proper input here. I think I don't even need to test and see if it is included, because I think, logically thinking, this is not included, because um, because if each root to leaf path in the tree represents a number, because when I say, so what are the leaves of this node, whenever I say what are the leaves of this tree, then I would say 3, 1 and 0. I will not say 3 null, 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 right? So that is why I think that only the this would be considered. So only the null leaves should not be considered. This is my assumption. Are they even leaf nodes? Okay. And so if this is not considered, then what I was thinking, I can just do DFS, right? 4 9. So when I do post or pre or DFS, then first of all I would go to 3, and then when 3 is returned, then 3 I'll return 3 to 5, and then when 5 when returning from 5 to 9, I return 5 3 to 9. Whenever I'm returning from 9 to 4, then I would return 9 5 3 and 9 1 to 4. So yeah, that was what I was thinking. So it would be 3 5. So whenever I'm returning to 4, then it would be 9 5 3. I'd be returning to 4, and I'd be returning 0 to 4, right? So it would be 4 plus, if this is a string, then it would be 4 plus 9 5 3, and it would be equal to 4 9 5 3. So at last, whatever is the value that is returned to, I mean, yeah, it means that at last whatever is returned, at last all these values will be written, right? It will be written 4 9 5 3 and 4 4 9 1 4 0 will be returned, right, at last. So I need to add all of these at last. Okay, so it means that at every node, at every the recursion function, it will return a string that is formed till now. So until 5 will return the string 5 3 to 9. So every child, when it is returning the value to the parent, it will return the string that has been formed till now. So 4 will return 4 9 5 3 4 9 1 4 0, and 9 will return 9 5 3 9 1. Yeah, so if this was the case, why, suppose then like 9 would return 9 5 3 9 5 5 1 9 5 5 2. So there might be so many paths, right, that lead to the leaf node. From every node there might be 1 2, I mean, so I'm thinking about time complexity. So because this will be like an array, this will be stored in the form of array, so space complexity would be, because how many paths can there be? So if h is the height of the tree, then there can be, so if this is the first node, then can be 2 3. So at every branch there are 2 branches, right? So it will be 2 to the power h. So space will be 2 to the power h. Space complexity will be O of 2 to the power h, right? Because if the height is 0, then it will be just If the height is 0, then it will be just 2, but it will be multiplied by 2 at every time. So there is 1, then 2, then 2 into 2, then into 2 into 2, so 2 to the power h space complexity. So there will be the array will be of size 2 to the power h. 2 to the power h. So the main root will return the array with the size 2 to the power h, and I need to add the elements of the array at the last. So yeah, so first of all, let array is equal to empty, or anyway, I mean const, I can say const array is equal to find paths, find root to leaf, find root to leaf paths. That is a function, and I would pass root in the beginning, and then I would also add all the values, add all values in array, and return the sum at last. But before that, I will write this function. So function would be, if this is a root node, then if this is a node, then first of all I would go till the last, right? And then whatever is the value that will be returned. So if it is 3, then 5, so 3, I'll return 3, and from 5 I return 5 1 and 5 2. Okay, and from 5 I return whatever the value that I've got. So it means that at last I would return the array, right? Yeah. So from the left I would return something, and I would attach to that node value, and from right I would also return 5 1 5 2 and attach to its 5. So it would be like return array, and first of all constant left is equal to node.left. So I would also get a list of values from left and from right as well. Find root to leaf paths node.right, right? And what I'd do is I'd create a new array is empty in the beginning. Our array is like left, because whatever I get from left, I need to attach, right? I need to attach 5 to all the values that I get. So how to do that? I would have to, for constant L of left, I would have to array dot push node dot value plus L, right? So this will give me all the values, and even for right also I need to do the same. For R of right, I need to pass node dot value plus right. So what that will give me is, so suppose if I'm at node 5, then the left will return 3, so it would be 5 3, and right would return 5 1 and 5 2. So 5 would be attached 5 5 1 5 5 2. So that is what will be returned. That they will all be the string. And yeah, and this will be returned. So what are the base cases? So I wrote the recursive relation, and the base case would be whenever I hit the base case would be, suppose if there is 1 and then node dot left, what will left return? So if there is nothing, if it is null, then it should return empty string. So this is the base case. So if there is 1, then this will return empty string. So 1 plus empty will be this will return 1, and yeah, this will return this 2 only, and of course And even if for this case also, so 5 will return 5 1. And oh yeah, so when I'm looking into the 5's left, 5, so whenever I'm looking here, then this will be 5 1, right? So this will, I mean 5's left will return 1. So whenever I'm merging, then it will be 5 1. And 5's right will return empty. So whenever I'm merging, then it will be 5. So whenever this is returned, whenever I'm returning from the child to the parent, then this will be returned 5 1 comma 5. So it means that this is also considering the null value as a root. So yeah, and another thing is, whenever there is a empty node, two empty nodes, then since left is also returning empty, right is also returning empty, so there will be double one here, right? So in this case, left will also return empty string, and right will also return an empty string. So this would actually, I think what I can do is, I can just, instead of returning empty string, I can maybe, can I just return empty array? If I return an empty array, then it would be, because if I'm it, or can I just return a empty string in the array? Because if I return the empty string here in the array, then it would be, I mean, if this is empty string, this is also empty string, because this is also null and this is also null, then it would be like, if there is one node, then the array would be, from this side also it would be returned empty. I mean, so one would be added two times, right? From this side also, from left side also, from right side also, but I only need it to be added once. So what do I do? Can I, maybe I can just do note that, maybe I can just, add first of all note that value in the beginning. So whatever I get, maybe I can just add, I was just trying to, so whenever, so if this is returned, right, and suppose if I want 5 to be attached to this number, then what would I do? Yeah, this is not possible. So I'm just trying to find a way to, if there is a null value, then I do not want to add, so if there is a null value, then I do not want it to be added twice. So this will also return empty, this will also return empty, so I do not want it to be added twice. There is a, I mean, if it is just empty, then it would not return anything, it would return empty array, because left is also not returning anything and right is also not returning anything, so it would return an empty array 1. But suppose if just one value is empty, then first of all, I just want to verify that this assumption is true. Is null node also considered a leaf node? Is null a leaf node? A node is a leaf if both left and right child of it are null. So it means that null is not a leaf node. Okay, so this is true. It means that what I can do here, if that is true, then I can just say that if node dot left and node dot right, if it has nothing, then you know, then it means that it is a leaf node, right? So if the node does not have a leaf node, or if node does not have a left node, if node doesn't have the right node, then it means that if it is a leaf node. So I can just return node that. So in that case, I can just return the value. So in this case, 1. So 1 is a leaf node, so it doesn't have left is also null, right is also null. So I can just return 1 in this case. So that's what I did. If both are null, then it means it is a leaf node. So this case is done here. And what about this case? So since this is null, what if 5's left is done but 5's right? So I should also consider that. So if a node is null, then what should I return? Then I think that I guess I should return empty in this case, because if the node is null, then I should return empty so that it wouldn't be added, right? So in this case, 1 would be returned and right would need to return empty array. So when 5 returns to its parent, then it would just return 5 1 only. It do not return 5 again because this is empty, and we are not pushing anything to array for empty array. Okay. I think this is okay. I think this would work, but I think we can still optimize this question, because I'll just write optimization at last. Optimize it so that we don't have to create new array every time in the recursion function. So I will think about this later. First of all, let's complete the code. So let sum is equal to 0, and for constant as of sum, for constant as of array, I would add sum is equal to sum plus numbers as, sorry. So I just changed the, because that would all be the string. So I just changed the number to, so I just changed the string to number. Okay, and at last return sum. So I look at this from the beginning. So first of all, I just found so this function, what this function would do is return the array of all the strings formed from root to the leaf nodes. Okay, from root to leaves. So this is what this function does. It returns all the all array of all the strings formed from root to leaves. So for this one, for 9 it will return 95 and 91, 95 comma 91. For 4 it will return 495, 491, 40. So yeah, if node is empty, then it will just return empty because there is no any strings formed. And if it is a leaf node, then it will return just that value only. Okay, and left and right. So this is an array that we want to return here, and we are pushing the value. So whenever since 995 will return, so I need to attach 4 before 95, right? So that is why I'm attaching here 4 before 95. And here I'm attaching the value of the node before all the paths that are informed till now, till that. I think this would work, isn't it? Okay, surprisingly this worked. Not surprisingly, but I think that I can still optimize it, because I'm here. I can see that I'm building array for every time. Can I do this more efficiently? I don't think so, because whenever I find a array, then I need to attach it, right? I mean, if it was just one value, then I could have done left plus. I mean, then I could have done. I mean, then I could have note that value plus at this point. But since this is a array of the path, so I need to loop over it. That is why I think this is the optimal case. So the space would be O of 2 to the power h, and the time complexity in this case would be the array value. Oh, sorry, the time complexity, space complexity in this case would be O2 to the power h, and the time complexity would be, because we are just passing through all the nodes once only, so it would be O of n, where n is the number of nodes. Okay, thank you for watching.